Okay, today we're going to talk about titrations. And titrations is one of those concepts that really gives students fits. And the reason is because it's really building on everything we've talked about in buffers and equilibrium and acids and bases, and now considering changing the volumes of the acids and bases and figuring out how that is affecting pH. So there will be a lot of ice charts, sometimes multiple ice charts in a single problem, and it just really takes a meticulous student to keep track of it all. So today we'll talk about strong acid, strong base titrations. In future videos, we'll talk about weak acid, strong base, or weak base, strong acid titrations. So let's first sort of define what a titration is. Okay, in a titration, this is all about really being an experimental lab and thinking about some unknown concentration of strong base, like shown here, or strong acid down here, and adding to it a known strong acid or strong base. So maybe we know this is like 0.4 molar HCl up here in the burette. And what we're trying to figure out is, what is the strong base concentration down here? And by slowly dropping in H plus and neutralizing some amount of OH minus that is in this strong base, eventually we will drop by drop add exactly the right amount to neutralize all of the base down here. And we'll be at the equivalence point, which is defined where moles of acid in the solution equals moles of base. And so in an experimental sense, the whole point of a titration is to add exactly the right number of moles of acid to reach the equivalence point, where you will then know what the moles of base and thus molarity or strength of the base is. Because we know the molarity of the acid, we're keeping track of how much we're adding, so we know the moles of the acid, so that when we reach this special equivalence point, we can then easily work out how many moles of base is it, because we know how many moles of acid we've added. And we know the volume down here, the base, so we can figure out the concentration or molarity of this base. So a titration is all about adding some known acid or base concentration to an unknown acid or base in order to reach the equivalence point and use the information of moles of acid equivalent to moles of base to figure out this unknown. Now, I'll note first, for strong acid, strong base, which is what's represented here, the equivalence point is always going to be 7, exactly neutral. Because if you add the exact amount of H pluses to exactly neutralize all of the OH minus in that strong base, all you're going to be left with is pure water, where the equivalence point will be 7. That will not be the case for weak acids or weak bases, as we'll touch on in future lectures. Now, as I mentioned, there's 3 types of titrations. Actually, there's 3 types we'll cover. There's a 4th that can be weak titrations we won't cover in this course or these videos. Today we're only going to concentrate, or in this lecture I should say, we're only going to concentrate on strong acid, strong base. In future videos we'll touch on these other 2. So let's first think about, sort of pictorially here, 4 different situations. If we're going to be adding, let's say we have a strong base in my burette up here, which is all OH minus. So maybe it's like 1 molar sodium hydroxide or something that we know. And down here is my unknown acid solution, where there's some amount of H pluses floating around. How much? I don't know, but let's pretend we know. And I should note, as we move through this, as I said, the point of a titration is an experiment to determine an unknown concentration. But what we're going to be doing in this video and subsequent videos is really instead calculating the pH anywhere along this curve and thinking about, if I knew the concentration of base and I know how much acid I add, how would I work out what the pH would be, and really try to understand the shape of this curve and calculate the pH anywhere along it. So with regard to the problems we're going to be solving, it's going to be giving us information about the concentrations of the acids and bases, how much we're adding, and what the pH then will be, right? So if we've added 10 mils of 0.4 molar HCl to this 1 molar solution of sodium hydroxide, what would the pH be, for example? Okay, so let's just walk through sort of 4 different steps here. Maybe we know the concentration of the strong acid down here, and we know the concentration of the strong base down here. And we're going to be worried about figuring out what is the pH then after we've added, say, 10 milliliters of the strong base to 50 milliliters here of this strong acid. But let's worry about sort of 4 different places we could be throughout this titration process. Okay, and these will be sort of the 4 different types of calculations we'll have to do for a titration. The first is, let's just think about at the start of the titration, before we've added any of the strong base. Okay, so you might be asked in the context of a titration, consider the following titration. What is the pH before any titrant has been added? Okay, so that would correspond to this first case we're going over here now, where all you have then is just a strong acid sitting there. So the pH of a strong acid is going to be something very low. And if we knew it was 1 molar HCl or 2 molar HCl, we'd just take the negative log of that strong acid to get the pH, because we haven't added anything to it yet. So this pH is going to be low. We'll just say it's something like 1. Okay, so this is before the titration has started. We are going to calculate the pH in these examples, how we've learned in the past to calculate pH of a strong acid, or in future videos of a weak acid just sitting there without anything added. Right? For a weak acid, you need to know the Ka. For a strong acid, you don't need to know the Ka. It's just negative log of whatever the concentration is of that strong acid, of the HCl, for example. So that's sort of the first place in the titration we could be before we've started the titration. And so we're also going to think about sort of one of these curves here, as shown here, pH versus volume added. Right? In this picture, we have volume of base that we're adding, right? This OH minus is what we're going to be adding. And the y-axis here is pH. And let's start with 0 milliliters added. So we are right here on this baseline. The pH is going to be something like here. Maybe this is 1. Right? Before we've added anything, any volume of base, it's just a strong acid sitting there. It's going to have a low pH. Let's assume it's 1 for this example. Okay, so that's sort of the first place or first type of titration problem we could be asked. Type number 2 is now we're going to be adding a little bit of the base. Right? So we still have the same strong acid down here. H plus, move it over a little bit. H plus, H plus, H plus, H plus, H plus. So there's still this strong acid down here. And we still have this burette of strong base above it with all of its OH minuses floating around. And now I'm going to put a couple drops in. Okay, so I've added a couple OH minuses. Those will neutralize my H pluses. Right? So now I have neutralized a couple of the H pluses in there. What is the pH going to be? Well, it's going to be a higher pH, right? Because there's less H pluses around, it is going to be slightly more basic after I've added a strong base to it. So the pH will go up a little bit, maybe to 1.5 or something, okay, as we move to the right on this curve and add more and more base. And if I added another drop, it goes up a little more, and another drop, it goes up a little more, as each H plus is being neutralized by an additional OH minus. Okay, so we'll just say the pH is maybe 1.5 at this point. So this is sort of the second type of titration problem you might be added, when you have some strong acid or strong base sitting down here, and you've added some small amount of the strong acid or strong base to it. And the pH has then, in this context, risen. Okay, but we're definitely before the equivalence point. We haven't gotten rid of all of the H+. Remember, equivalence point, which is the third example we're going to be talking about, is where we will neutralize all of the acid in this example with the precise number of required OH minuses, or strong base in this example. Okay, so this is the start of the titration, was the first type of problem. The second type is when you're started the titration and added some, but you're still before the equivalence point. The third type is going to be, now we're going to be at the equivalence point. Okay, so let's look at this. We have some strong acid, H+ is floating down here, and we've already added enough OH- to get rid of 3 of them, right? So we're continuing to add our strong base. And now we're going to be asked to be at the equivalence point. So we've added exactly, in this example, 5 OH- to exactly cancel out the 5 H+. Right? And this is all being done sequentially. So, at the second point here, I've added enough to cancel out 3, and now I have 2 left. And now at the equivalence point, I've added exactly 5. In a practical sense, obviously the amounts will be much, much greater. I'm just showing this because I only want to draw 5 H+ and not, 5 times 10 to the 22 H+ or something like that. So now we're at the equivalence point. What's left? Well, if this is a strong acid, sure, maybe there's some like Cl- floating around still. And if it's a strong base, like sodium hydroxide, maybe we've added some Na+, right? But remember, like, those are spectator ions. Okay, we've canceled out all of the H+ acid and OH- base. All that's floating around are these spectator ions, which don't behave like acids or bases. They don't affect the pH. Okay, there's also water in here because it's aqueous. And so this pH will be exactly 7 because there's no H+ or OH- floating around. Okay, so now at some volume, you're going to reach the equivalence point, and you'll be at a pH of exactly 7. Okay, and the way that this typically runs is you get a slow rise, and I should really draw this a little bit more like this. It goes up very slowly, so maybe 1.5 is not right. Maybe this is more like 1.1 or something. And then it sort of exponentially goes up through the equivalence point. And then it'll kind of level off. Okay. And the reason is because once you get near the equivalence point, every additional OH you add really drastically changes the amount of H+ there is. Right? When there's only 2 H+ left, and we add 1 OH-, we've cut the amount of H+ left in half. That's a big change. And so the pH changes rapidly near the equivalence point. Exactly at the equivalence point will be exactly at a pH of 7 because there's no H+ or OH- left. Okay, and the fourth type of titration problem we could be asked is after the equivalence point. So now there's no H+ left, but we continue to drop OH- in. And so in addition to sort of the spectator ions and the waters that are floating around, well, now we've added too much strong base and we're adding OH-, just pure OH-, no H+. So this thing's going to become very, very basic. And the pH will be something high, like 10 or 11. Okay. So this is the start of the titration. First type, second type, we're somewhere in here. Third type, we're at the equivalence point. And fourth type, we're somewhere out here. All right, so that gives you an idea of conceptually what we're doing in a titration. And we need to be able to calculate all 4 of those types of problems. start, before, at equivalence, and after equivalence. And the shape of the curve will look something like this when it's titrating a strong acid. Down here in the beaker, there's H pluses and Cl minuses with your strong base. Okay, so that's what we're talking about here. We're titrating a strong acid with a strong base. So this kind of verbiage tells you what's being added to what. What is the known thing and what is the, thing sitting in the beaker down below. Titrating the strong acid sitting in the beaker with the strong base in the burette. Okay, so at the start of the titration, nearly up to the equivalence point, the pH goes up slowly, and then just before and after the equivalence point, it really starts to rise rapidly. Here, the pH at the equivalence point will be 7, and after it'll continue to rise and then sort of level off. Okay, and pictorially, as we discussed at the beginning, there's only H plus and Cl present, right? That was before the titration started. As we add OH minus, H plus is consumed, so the pH goes up. There's less acid around. At the equivalence point, we've added exactly the right amount of OH minus to neutralize H plus. So there's no H plus or OH minus around, just some spectators and pure water, so the pH is 7. And then after the equivalence point, we've added excess or extra OH minus. And so the pH will be something quite high because now it's a very basic solution. Okay, so that's everything there conceptually. I'll just quick note that if the situation was reversed and we instead had our base down here to start with, that we were adding an acid to, well, the curve is similar, it's just flipped. Because at the beginning of the titration, we're starting at a very high pH with just base around. And we begin neutralizing some of that base, so the pH drops. It gets less basic. And then at equivalence point, we've neutralized all of it. Our pH is 7. And after the equivalence point, we've dropped in now too much H plus. And so we're making a very acidic solution with a pH of like 1 or 1.5 or 2 or something like that. Okay. Now, we need to learn how to calculate any of these 4 types of problems for strong acid, strong base. Before equivalence, before the titration begins, at equivalence, or after equivalence. And we're always going to be wanting to calculate the same 6 things here. Read through the problem and calculate how many moles of acid you have, then calculate how many moles of base you have. And then after they neutralize one another, what is left? So we're getting an ice chart involved. We'll also have to worry about how the volume of the solution is changing, right? Because remember, what we're doing here is actually dropping a volume in. And so I guess I should draw this as the volume getting higher and higher and higher because we're adding more and more liquid to the beaker throughout this titration. So we do have to keep track of the volume of the solution and calculate the new concentration at the end of the H plus or OH minus that's still floating around and what the new pH will be. Okay, so one thing to highlight here is, in contrast to a lot of previous ice charts we've done, we really need to be using moles in our ice charts. Okay, and the reason is we can't use molarity because the volume is constantly changing throughout the titration. And molarity is moles per a certain liter, and the liters is changing. So in our ice chart, we are going to be using moles. That's why the first 2 steps here are to calculate the moles of acid and moles of base. Okay, enough delay. Let's jump into a problem. Calculate the pH when 49 mils of 0.1 molar NaOH have been added to 50 mils of 0.1 molar HCl. Step 1, calculate moles of acid, and step 2, calculate moles of base. Okay, so I like to always just start with the moles of acid. Okay, and the moles of acid here are going to be liters times molarity, right? So 0.100 molarity times, converting that milliliters to liters, 0.050 liters, gives me 0.005 moles of H plus. Okay, remember HCl, I'm really just, it's a strong acid, thinking about it as H plus. NaOH, I'm really just thinking about as NaOH minus. And what I have here is, my strong acid, 50 mils of 0.1 molar, that I'm adding the OH minus to, 49 mils of OH minus. Okay, so I have to calculate my acid, done. I have to calculate my base, calculate it the same way. Point 0.0049 moles of OH minus. Okay, step 3, ice chart. But I'm using moles in my ice chart. And what is the reaction that's happening here? Well, I have an acid just floating there, which I'll call H plus, and I'm adding to it this base, strong base, OH minus. Those two things are going to neutralize each other to make water. And let's just make an ice chart based on this. H plus I'm starting with is 0.005 moles, not molarity. OH minus I'm starting with is 0.0049 moles, not molarity. And the liquid water, I don't need to keep track of the right side at all. Now, in a titration, what is happening? We're adding OH minus, and we're adding 49 mils of it. And what is it doing? It's neutralizing this H plus, okay? And it's going to neutralize as much of the H plus as it can. So in a titration, one of these things on the left side is going to be completely used up and neutralized. All right, so you just have to realize that the lesser of the two numbers here of the initial column is going to go completely to zero. That's what acids and bases do. They neutralize one another. So one of them is going to get completely used up. Point 0.0049 is less than 0.0050, so that's the one that's going to get completely used up and go to zero. The H plus is going to go down by that amount because it's been neutralized in a 1-to-1 ratio. So in the end, I will be left with 0.0050 minus 0.0049, or 0.0001 moles. Remember, it's not a concentration, it is just moles we're working with. And now we see why step 4 is important, the new volume of the solution. Okay, because we're going to have to take this moles of acid and determine the concentration, which is divided by some total liters. So now I need to worry about what is the total liters here, because I've dropped in 49 mils, and now the solution is not the original 50 mils, it's higher. It's 99 mils because I've added 49 to 50. So step 4 is my new volume is going to be 99 mils, or said another way, 0.099 liters. And step 5 now is to take the moles I've determined from my ice chart and divide it by this liters I just calculated. Okay, so step 4, determine the new volume, is just looking at the problem and adding together the volumes of acid and base, right? 49 plus 50 is 99 mils, or 0.099 liters. And so step 5 is now, what is the concentration of whatever is left? Well, there's H plus left, so the concentration of H plus is the moles that are left from the ice chart divided by that new volume. So this is the molarity I get. And overall, I'm asked for the pH. That's what these titration problems are going to be after. And so I just do negative log of that pH. And here I get a pH of 3. Okay, so I'm somewhere, maybe like here on the titration curve. I've added 49 of the 50 mils, so I'm approaching the equivalence point. My pH is now 3, but I haven't had enough OH to completely neutralize and get to a pH of 7. Okay, let's look at another type. So this was before equivalence. Let's look at after the equivalence point. Calculate the pH when 51 mils of 0.1 molar NaOH have been added to 50 mils of 0.1 molar HCl. Okay, so you see this is the same as the previous problem, right? So I've now added 2 additional milliliters. Okay, so I'm going to be doing the same thing. Step 1, moles of acid is going to be the same, 0.005 moles of acid. But now I want step 2 to be 51 milliliters. Okay, so now I'm going to have step 1, moles of acid is still going to give me this, 50 mils at 0.1 molar. Step 2, 0.051 liters times 0.1 molar is going to give me 0.0051 moles of OH minus. I'm still going to make the same ice chart here. Still the same H plus, OH minus to make H2O. And your ice charts for these strong acid, strong base titrations will always look like this. H plus, strong acid, OH minus, strong base, makes water. So we don't keep track of it. And now I just have to enter the moles in the problem. One of them gets completely used up. Which one? The lesser of the two, which in this case is the acid. That is what's going to get completely used up, and I will have excess base. My volume that is resulting is 51 plus 50, 101 mils, or 0.101 liters. And so my new concentration now, what is left? OH minus. So I'm calculating a OH minus concentration based on the ice chart moles that I have left, divided by this new volume. And I get something like 0.001 or close to it molarity. Negative log of this OH minus concentration is my POH of 3. And I can get the pH then by doing 14 minus that to get 11. Okay, don't forget that final step. Remember to write this out. What are you working with? What do you have left? It's OH, so negative log will give you a POH that you then convert to what's asked for, pH. Okay, now, if the problem had asked for 50 mils of 0.1 molar, there would be 0.005 moles of each. And you could just stop at that point and see that moles of acid and moles of base are equal. That would be at the equivalence point. And you can just stop and say, well, it's strong acid, strong base, pH is 7. Don't have to do anything else. Okay, so always go through the motions of calculating moles of acid and moles base to start these. If those two are equal, then you're at the equivalence point, and the pH is 7 if it's strong acid, strong base that we're covering in this lecture. Okay, but here that wasn't the case. We had added too much, 51 mils, to give us 0.0051 moles, and we were left with some excess moles of OH, which we turned into our molarity and got to the pH eventually there. pH is high, it's basic, which makes sense because we've gotten rid of all the acid and we have excess OH minus. Now, we covered before equivalence, after equivalence, and then I had a brief aside there if it was at the equivalence point, pH is 7. What about if it's just before any titrant has been added? Calculate the pH before any NaOH has been added to 50 mils of 0.1 molar HCl. Well, remember, then this is just a strong acid. Nothing's been added to it yet. Okay? If this is 0.1 molar strong acid, I would just ask you to consider what is the pH of 0.1 molar HCl. So strong acid, we just can immediately do negative log of the concentration of that strong acid. because really this HCl is all H+. So it's just negative log of this 0.1 molar. So the pH will be 1. Okay, so before the titration starts in these strong acid, strong base problems, the pH is pretty easy to calculate, negative log of the molarity of the strong acid. But once you start adding stuff, well, then you have to get ice charts involved and figure out what's neutralizing what's left over, what is the new volume, what is the new molarity, get to the pH. Okay, so this is the last slide I have in this lecture video, and this will take you through each of the 4 different regions we talked about. All right, so now we have 40 mils of 0.1 molar HCl, and we're going to be calculating it at the start of the titration before anything's been added. After a little bit of OH has been added, so we'll be before equivalence. We'll, in part C, be at equivalence, so you should be able to predict right away what the pH is there. And then in part D, we'll be after equivalence. Okay, so I would pause the video here and really try to go through each of these to calculate the pH. And then I'll proceed and solve it a little quickly. Okay, so let's read through this. We have a solution of HCl, so that's really just H pluses. It's 0.1 molar. And there's going to be some OH minus up here that is 0.1 molar that will be dropping into it. But part A is before we've dropped any in, so it's just 0.1 molar strong acid. The pH there is negative log molarity of that strong acid. That equals 1. Okay, and all the rest of these, we will start considering moles of acid and moles base. All right, so let's go through each of the remaining ones. That part A is quite straightforward. The titration hasn't started. Why? Because we haven't added any of the titrant. So it's just the strong acid sitting there. pH is negative log of that strong acid concentration. Now, part B, let's start with calculating the moles of acid. Because now we're going to be adding some base to it, and the volume is going to be changing. So we have to do all 6 steps here. Moles of acid, well, 40 mils of 0.1, you should get 4 moles of H+. Moles of base, 10 mils of 0.1 is 0.001 moles of base. Ice chart, where the ice chart for all these strong acid, strong base is going to look just like this. These are our initial conditions we've calculated. One of these will get completely used up. Whichever one is left gets completely neutralized. So the OH is left, is less. So that'll get completely used up or go down by 100%, 0.001. H plus is being neutralized by that in a 1-to-1 ratio. So it goes down by that much. And so I'll be left with, in this case, 0.003 moles of H plus. And I'll want to then calculate the concentration now of that H plus, which is going to be the moles divided by the new volume. The new volume here is 10 plus 40, so 50, so 0.050 liters. And so now I have the concentration of H plus, 0.06 molar, and I can take negative log of that to get a pH of 1.22. So that will be the answer for part B. Part A, pH of 1. Part B, well, we've added some base, so the pH better be a little higher, and it is 1.22. Part C, moles of acid, still 40 mils, 0.1. Moles base, now it's 40 mils of 0.1. That is also going to give me 0.004. And, oh, alarm bells are going off. Moles of acid equals moles of base. This is a strong acid, strong base problem at the equivalence point. pH is 7. Don't have to do anything else. Moles of acid equals moles of base. Strong acid, strong base, pH 7. Done. That won't be the case for weak acid or weak base titrations we'll talk about next lecture, but it's the case here. All right, so we've done part C. And now part D, 50 mils of NaOH have been added. Okay, well, let's calculate moles of acid. Still that same 40 mils at 0.1 molar. Moles of base is now 50 mils at 0.1 molar. So that should give you 0.005 moles of base. Now I'm going to enter that into my ice chart. Working with moles in my ice chart, always in these titration problems. And then I look at 0.004 and 0.005. The acid is less, so that is what's going to get completely consumed. In other words, go to 0 at equilibrium. Therefore, the change is minus 0.004. It's a 1-to-1 ratio between my acid and base, so my base will be going down by that same amount. And so that'll leave me with 0.001 moles of base. So I'm after the equivalence point, I have neutralized all the acid, and I have some base left. So I'm expecting a high pH here. My new volume is going to be 50 mils plus the original 40 mils of acid, so 90 mils, or 0.090 liters. And I can worry about calculating the concentration of what is left here. What is left is OH minus. So I'll be calculating the OH minus concentration here. Moles at equilibrium divided by this new volume. And that'll give me 0.0111 molarity. Finally, I can get the negative log of this OH concentration, which will be telling me the pOH here. And negative log of 0.0111 molar is going to give me 1.95. Therefore, the pH is 14 minus 1.95, or 12.05. A high pH, a basic solution, which makes sense because we are after the equivalence point. Okay, so in this lecture video, we've introduced the concept of strong acid, strong base titrations, and done lots of different examples here of all the different types or parts of a strong acid, strong base titration you could be expected to calculate. Next time, we'll get into the more difficult weak acid or weak base titrations and discuss how we need to get Henderson-Hasselbalch back involved and multiple ice charts for equivalence point problems. But that's it for this lecture. See you next time.